In the second video, I'm going to introduce to you some of the other CAD classes that we offer. And I'm going to talk a little bit more about CAD 5 and also some of the other classes offered in other departments. Okay, so CAD 5, so it's 2D drafting, and we are using AutoCAD. Even though AutoCAD can do 3D, we're not going to do 3D in this class. The advanced AutoCAD class that we used to have 10 plus years ago has been replaced with Inventor and SolidWorks. Even though AutoCAD can do 3D, it's not the preferred software when it comes to 3D. AutoCAD is pretty much the most common and one of the oldest softwares out there. It's been around for decades. It's well known, and for 2D, it's the software to go with, and because it's affordable. And to show you the difference, those of you that are not familiar with 2D versus 3D, let me show you a visual just to get the point across. So when you think of The Simpsons, here we have the cartoon drawn on a flat plane, or obviously a plane is flat. So just like a sheet of paper, you're drawing. So this is a 2D cartoon of The Simpsons, and there is an episode where Homer goes into the third dimension, right? So here's Homer in 3D. Okay, so now it's out of plane. It's in the XYZ direction. Okay, so this is 3D versus 2D. Okay, so in CAD 5, we're going to be doing only 2D. Okay, we're going to be creating all our drawings on a single plane. In this case, we'll be drawing on the XY plane. Okay, so CAD 5. So CAD 5 students seem to have very diverse backgrounds. So I have students in CAD 5 that come from different backgrounds. I have students that are still in high school or just out of high school. Some already know, hey, I want to learn more about CAD. This is the industry I want to go into. Others are just giving it a try, see if they like CAD. I also have local students that either work at your local machine shops or even furniture making shops. So I have students with different backgrounds, from students working on custom furniture and they want to learn CAD, or working on furniture for the big casinos. And also, again, as I mentioned, the local machine shops and metal forming shops, they work manually at the shop and they want to learn some CAD skills and move up in the company. And also get sometimes engineers from the local aerospace companies or even automotives, such as Toyota, for example, or Northrop. Usually that's in my other CAD classes, the more advanced classes. But sometimes I do get them in the CAD 5 class. And sometimes I get students that are retired. They want to work on personal projects and they want to learn some CAD skills and model up their ideas. And again, sometimes I do get architecture students. You're more than welcome to take this class. And in some cases, even electrical students. We don't cover electrical, but I will go over some of the symbols that are used in other fields such as architecture and electrical and also welding. All right, so CAD 5. So what does CAD 5 look like? So the next visuals I'm going to show you, I'm going to show visuals that I downloaded from the internet. And some of the stuff I did work on, a lot of the stuff I did not. It's just some cool visuals I found on the internet to relate these softwares and where it's used out in the real world, outside of the classroom. All right, so let's take a look at AutoCAD. So this is just a visual that I downloaded from the internet. So here are the three views are modeled in 2D. Now, even though this is an isometric view, in the old days, we would model it in 2D to make it look like a 3D object. Now, because of 3D now being more popular now, we tend not to model isometric views anymore. We did in the past. I'm not going to have you model isometric views. We are going to have one handout on how to draw isometric views, sketching by hand, but we are not going to do it in AutoCAD. We're just going to be creating simple views, 2D views like you see here. Okay, so this is AutoCAD. and it's owned by Autodesk. And again, as I mentioned, AutoCAD is not the preferred software for 3D. So Autodesk, to be able to compete, came out with Inventor. So Inventor, 3D modeling, very affordable. They also have this software at the high school level and some of the community colleges like us. It's a very user-friendly, affordable software. So that's the CAD 7, I believe, Inventor 3D. I have not used Inventor in, must have been 12 years. Okay, so outside of the classroom, I never used Inventor. I am familiar with it, but I'm rusty on Inventor. Okay, the next one, SolidWorks. Okay, SolidWorks is more powerful than Inventor. And again, as I mentioned, Inventor, it's affordable. You see it at the local high schools and local community colleges. For small stuff, robotics, for example, simple parts that are not too large in file sizes, Inventor is awesome. Now, if you need something to maybe design a large drone, for example, medium or small aircraft, maybe like a 2-seater or 4-seater aircraft, then you need to start moving up to something like SolidWorks. SolidWorks is more expensive. I don't remember the exact price for the license. I'm thinking somewhere around $5,000 to get the license for SolidWorks. I may be off on that. Something you can look up online. Definitely a lot more expensive than Inventor. And SolidWorks, let's take a look at SolidWorks. So here's SolidWorks. Again, a picture I downloaded from the internet. SolidWorks is owned by Dassault Systems. So you see the DS next to SolidWorks. Okay, Dassault Systems. So some of the companies that model simple shapes or files that are not too large. For example, I worked for companies that did small drones for the military. Those small surveillance drones that a soldier can just hold on to it and then just throw it up in the air just to give it enough push so it can get enough momentum to start flying on its own. Okay, so SolidWorks is a very popular software. Also, again, as I mentioned, for simple geometry. So where I'm currently working at, currently we're working on a lunar lander, and we're using SolidWorks. This lander is about maybe 10 feet in length. The geometry is very simple, very geometric. We're using hexagons, for example, triangles, cylindrical shapes, and trusses, triangular trusses, for example. So when it comes to simple shapes and files that are not too large, then we go with SolidWorks. Okay, now I have worked for companies that started a project in SolidWorks, and especially for something larger, like a very large drone with the wingspan of 165 feet, and I'll show you that later on in a later slide, where it was started in SolidWorks, but SolidWorks just couldn't handle the size of the files, and also it didn't have some of the workbenches or modules or apps that CATIA has. For example, CATIA has the composites workbench, for example, and it can handle larger files. So the next one, I'll come back to this one, is CATIA. Okay, so CATIA is a more powerful software. It's more expensive. A basic license can be $11,000, but if you want to get the most common workbenches, you're looking at about $15,000. If you want the full-blown license with all 100 plus modules and apps and workbenches, you're talking about $100,000 just for one license. But most companies will get the basic $15,000 license. Okay, and so for CATIA, we have half semester courses or 8-week courses. So we have 4 courses, and again, they're half semesters. We have a CAD 31, also taught online. We have CAD 32, the second part of CATIA, and that typically is taught in the second half, during the second half of the semester. I teach it during the fall. I think another instructor will be teaching it this semester. And then we have like CAD 33 that does kinematic simulation, stress analysis, etc. So that's CAD 33. I think we only offer this in the fall. And currently I'm teaching CAD 37. That's a surfacing. We cover the surfacing module or modules. That's an 8-week course. That's the course I'm currently teaching on Saturdays. It just started this past Saturday, and it's only for the first 8 Saturdays. These are 2 units each. Okay, so let's go back. Okay, so who uses this more powerful CATIA software? Companies such as Boeing, Toyota, Honda, GM, Ford, Lockheed Martin. So when you start designing these large commercial aircraft or fighter planes, you want to go with the more powerful software, but you're going to have to pay more for it. All right, so I skipped one slide. Let me go back. Also, we offer Mastercam. So those of you that work in machine shops, when you want to make a part, typically you start with the block. It could be a block of steel, aluminum. It could be remboard or wood. Typically, we machine aluminum. Okay, so we need somebody to program the FADAL or the Haas 3-axis. So if you go to YouTube and do a search on Haas, H-A-A-S, 3-axis machine, or if you go to look up FADAL, F-A-D-A-L, machining, and you get some cool YouTube videos of how things are machined. So you need somebody to programming. This is NC Programming, Mastercam. Most machine shops that I worked for used Mastercam. Even though CATIA has a workbench for NC Programming, it tends to be more expensive. And the only ones that really use the CATIA NC Programming are typically the ones that can afford it. So sometimes, for example, hey, we're going to work on this new fighter plane. Sometimes there's a collaboration between 2 different companies. It can be like Northrop with Lockheed Martin or Boeing with Lockheed Martin. And they have to agree up front which software are they going to use. So if they say CATIA, then everything has to be done in CATIA. The design, the drawings, the tool design, the composites, the NC programming for machining. Okay, so typically the military projects, they tend to go with one software because they don't want any problems with transferring data from one software to another. Okay, so back to Mastercam. So Mastercam is not part of this department, but we do share the computer labs. Okay, let me go down. I'll come back to the others. So Machine Tool Technology, the MTT department, they're the ones that carry Mastercam. Also in the Machine Tool Technology class, they have a blueprint class, blueprint reading, drawing reading, which is the same as CAD 5, but they're more into the machining part. Okay, and also they have a machine shop. So in the same level downstairs in the iTech building, when you see the double doors when you walk down the stairs, that's the entrance for the big, large machine shop we have downstairs. So that's in the MTT department. Also, they have robotics and programming. Our full-time instructor teaches those courses. Okay, so since we're down here, let's talk about a little bit about architecture. So architecture, I believe, is in the 2nd floor. They got lucky. They got the great view out the window. We're down in the dungeon, no windows. All right, so architecture, they have drafting classes where they do things the old school way, by hand, using drafting instruments, using T-squares and scales and triangles. So they still go with some of the old school methods of drawing, and they also have AutoCAD and Rivet. So Rivet is their 3D software. Again, it's affordable and it's pretty much customized for architecture. So Rivet is very similar to Inventor, but it's more tailor-made for architecture. But they all work in the same way. They're parametric modeling. Okay, let's go back. Now, some of you are probably asking, hey, teacher, on the first video, you showed us some of the topics we're going to cover, like orthographic projections and and front views, top views, and dimensioning, and sections, and tolerancing, and threads, etc., assemblies. I've already taken a class like that in high school, or I took a very similar class elsewhere, or I took blueprint reading. So if you've already taken a drafting class, then you can go ahead and jump to one of the other more advanced classes. Now, CAD 5, there are no prerequisites. Same thing with the other software. So CAD 7, Inventor, CAD 28, SolidWorks, and the CAD 30s, the CATIAs, it's only recommended that you take CAD 5. It's not a prerequisite. It's just recommended, hey, if you've never taken a drawing class or never looked at a drawing, a mechanical drafting drawing, then take CAD 5. But if you already worked in the industry, let's say you have 5 years experience, you already know how to read drawings. Maybe you are an inspector, for example. Well, yeah, I know how to read drawings. I inspect parts. I work for the quality department, so I know drawings. Can I just go ahead and jump into one of the other classes? And yes, you may. So CAD 5, it's not a prerequisite for the others. It's just a recommendation. So if you already have a drafting experience, hey, you're more than welcome to jump into one of the other classes that does the 3D modeling. But if you need credits for a graduation, you need credits for example, for a mechanical engineering degree, then you do want to stay in CAD 5 to get your credits. All right, so once we get into the 40s, then we're going into the more advanced classes. So the CAD 43, I think I may be teaching CAD 43 this summer. Will be my first time. So CAD 43 will walk you more into what do you see out there in the real world when it comes to design, the concept, what materials are you going to use? Are you going to use aluminum? Are you going to use steel? Are you going to use fiberglass? Are you going to use carbon fiber? What's my budget? What can I afford? What are the constraints? What are the prerequisites? So we're going to get into the conceptual side in CAD 43 for those that choose to take this class. And there's also an independent study class where you can design. You have a concept, you want to design it. I don't teach that class. One of the more advanced instructors teaches this class. And typically that's what you want, the more experienced instructors to be teaching the more advanced classes. So independent study, you're going to be working on a project, something you want to research and develop something. I don't know, maybe you want to develop a helmet and integrate some cool stuff in this helmet, example speakers and so on. Something that you can wear outside. I'm just throwing an example out there. Or maybe you want to design a futuristic or modern shopping cart. So I'm just throwing stuff out there. So that's CAD 99. Okay, let's go back to CAD 45. Okay, CAD 45, this is something you typically don't want to take at the beginning. It can be overwhelming. You definitely want to take CAD 5 first. Learn drafting first before you take CAD 45. CAD 45 is similar to learning geometry for the first time. It can be very overwhelming. Okay, so CAD 45 covers geometric dimensioning and tolerancing, also known as GD&T. And one of our more experienced instructors typically teaches this. I think the last and current instructor are both worked at Boeing, so they have a wealth of experience. Typically, a lot of the GD&T instructors worked in aerospace or worked in the quality department to inspect parts to see if they're made correctly and they're going to fit with each other. Okay, so what does GD&T look like? So let's go back to our visuals. Okay, anytime you start seeing dimensions with rectangles around them, right away you know there's GD&T symbols applied. Here's a frame here telling the machinist, hey, when you machine the surface, how much can you be off by? So this looks like a half circle or even less, saying, hey, this profile, the surface, you can be off by, from the model, you can be off by 15 thousandths. So you can be off by, typically, you cut this in half, so it can be 7.5 thousandths, 0.075, taller, or on the heavy side, or 0.075 on the lighter side. So actually it's 0.0075 on the lighter side or 0.0075 on the heavy side. That's roughly the thickness of a hair, or slightly bigger. The thickness of a hair is about 0.005, 0.004. Okay, so this is GD&T. Here's another frame, has a circle and a crosshair inside. That's telling the machinist, hey, the axis of this counterbore hole can only be off by 10 thou in any direction radially. So again, the thickness of a hair is 5 thou, 0.005. So where you need precision, you want to tighten it up. You can call it out in your GD&T, and then you have ABC. That's your axis. That's your XYZ axis for inspection and for machining, except we call it out with ABC. All right, so this is again something that is covered in the GD&T class, and I recommend that you do take it if you want to go into aerospace, automotive, machining, worked as an inspector for quality department. You definitely want to learn GD&T. I do use GD&T at work, not all the time, especially when I make drawings. I do have to use GD&T, but we're not going to cover GD&T in this class. And the reason for GD&T, why is it used? I'd say about 100 years ago, I think it was World War I, especially when countries go to war and they need to mass produce items for tanks and aircraft and jeeps, military jeeps, and mass produce bolts and nuts and washers. When you apply GD&T, it's a lot more precise way of inspecting parts. I believe it was the Germans back in World War I that came up with this GD&T approach, which is more accurate than simply using horizontal and vertical dimensions. All right. So I'm going to start sharing some of my experience. Again, the first visuals I've shown you is just pictures I found on the internet, and I will show you some examples of some of the work I've done or something similar to it. Okay, so roughly around 15, 16 years ago, my first job was taking a CATIA V4 models from, so these are models from Boeing and Northrop, and I worked in a local machine shop close to El Camino College. So one of my classmates recommended me for the job. So they needed somebody that can do drafting in CATIA V5, and I was just finishing up taking my CATIA classes. Those are the CAD 30s, 31, 32, 33, and 37 classes. So my job was to take the 3D model, like the one you see here, with these dimensions. Now there's dimensions missing. So even though I can open up the model, it doesn't give you all the dimensions. For example, what's this length? What's the thickness of these walls? It doesn't show it on this part. So a lot of the big companies like Northrop, Boeing, Lockheed Martin, the big aerospace companies, and maybe even some of the automotive companies, they don't provide drawings. They'll contact local machine shops or some of the machine shops that they work with. And when you have this part, like the one I'm showing you here, hey, we need this part machined. Typically, you send it out to 3 different vendors or machine shops, and they bid on it. Hey, what's the material? When do you need it by? How accurate does it have to be? How precise? That's tolerancing. That's where we have the GD&T for tolerancing. How much can you be off by? And then they bid on it. Well, how many parts are we going to make? Well, we need 1,000. Okay, so they bid on it. And typically you go with the lowest bid. But if it's, but sometimes you'll give it to the second lowest bid if they provide better quality and are more, and can meet their deadlines. So you don't always have to go with the lowest bidder. So my first job, I had to take models like this and turn them into drawings, 2D drawings, similar to, let me show you something like this. Now, this is a very complex drawing. This is not the drawing of the 3D model I just showed you, but just as an example, I would have to turn it into a 2D drawing to give to the inspectors and the machine shop. They need drawings that you can print out, take it out to the shop, and the machinist knows, hey, how slow they have to machine to be precise. If they don't have to be precise, then they can machine a lot faster to save time. Okay, here's another example. I don't know what software this is, of another part with attached critical dimensions and GD&T callouts. So if I wanted to know the length, here I would actually open the model as you see here, and then I would use my calipers to measure, and it'll give me the length of the edge. So I'm just going to make up a number. Let's say it was 4 inches. Then I would have to put that on the drawing. So any dimensions missing, you actually have to measure it. So when a Northrop or a Boeing offloads the work to a machine shop, the machine shop says, hey, what's this length? Well, measure it from the 3D model. Just use your calipers or your measuring tool here, and it'll give you the length. Let's say it's 5 inches in length. Well, how much can I be off by? Well, typically in the statement of work, part of the contract on a document, or somewhere in a hidden field here with general notes, it would say, hey, any dimensions, anything that's not dimension, use a tolerance of plus or minus 30 thousandths. Okay, that's 0.030 inches. The thickness of a credit card is about 0.020 inches, or an ID or credit card is roughly about 0.020. So you're pretty much telling the machinist and the inspector it can be off by a thickness of a credit card in either direction, on the heavy side or the light side. Okay, so I would have to create a 2D drawing of a front view, top view, side views, and any additional views, and throw in the dimensions. So I can pass it on to the shop, the machine shop. The machinist knows the tolerances and knows how fast or how slow they can machine. And also the inspector, when they're ready to check the part, they have a drawing. Now out in the shop and out in the quality department for inspection, they typically don't have the software. Let's say CATD. The company doesn't want to pay another $11,000 or $15,000 for somebody in the shop to view a model. So that's why we have viewers. It's called a viewer. It's a lot cheaper. It's not to model or design. It's just to view items, such as this one. But it's just easier if you just hire somebody straight out of college or with little experience, and somebody like me to make the drawings for them and then pass it on to the quality department for inspection and the machine shop. All right, so and again, here's another example that I found on the internet. All right, so obviously we're not going to make a drawing like the one I'm showing you. What we're going to learn in CADD 5 are just it's very basic. We're just going to learn the basics of drafting. And eventually, over the years, you're going to get better at drafting. You're going to start looking at very complex drawings and try to understand them. Sometimes you'll spend hours, sometimes days. Sometimes I've looked at drawings from the 1950s, 1960s that were converted to PDF files, and I'll look at it for 3 days before I understand what I'm looking at. Some of these drawings are very complex. Sometimes I'll take a highlighter just so I can distinguish one line from another, use different color highlighters, and that you'll just gain through experience. So we're just going to learn the basics, and hopefully in 5-10 years, you'll be able to simply read something like this and something a lot more complex. It takes experience to get better at this drafting. All right, so while I was learning, while I was creating drawings for this machine shop, so this shop created sheet metal parts for aerospace. The sheet metal you see around wings or the fuselage of the aircraft. So here's an example. This is not something I designed, but I've designed very similar tools like this. So this is an aluminum block. It's called a stretch forming block. So when you take a sheet of aluminum, it's very flimsy, just like a sheet of paper. It's very flimsy. And sometimes you're dealing with the thickness of about 30 thousandths, or 10 thousandths, Again, something the thickness of a credit card or double the thickness of a credit card, but usually around the thickness of a credit card. So these aluminum sheets, in order to form it to the shape of a fuselage or the shape of a wing, especially the leading edge of a wing, you need to take this piece of sheet metal and stretch it and change its shape. Okay, so just to show you how it works, here's another similar stretch form block. So you put a sheet of aluminum. So again, it's just a flimsy sheet of aluminum, just like a sheet of plywood or a sheet of paper. And you just lay it on top of this forming block. And then these hydraulic arms, you feed it into the hydraulic arms. So imagine these are vice grips and they're hydraulically controlled. So imagine, just simply imagine taking a plastic shopping bag, grabbing both ends with your hands, and then place it in over your knee, and you stretch it over your knee, and it'll fight until it gets the shape of your knee. Okay, so it's pretty much, this is what's happening here. Imagine these hydraulic arms. They're going to pull. They're going to hydraulically, like vice grips, grab the edges, just like your fingers, and then they're going to pull back. So here you see this cylinder. It's going to pull back. It's going to stretch it. And imagine this is your knee. And you stretch it to the point where you permanently deform it, and it'll grab the shape of the mold, this stretch form block. So those of you that have taken engineering classes, pretty sure your instructor talked about Hooke's law and the graph. You can push on something, compress it. You can put tension on it. Imagine taking a ruler, like a 12-inch ruler made out of metal, and you play with it, like you arc it, you push on it, you pull on it. So the metal or the material has memory and it goes back to shape. But once you overdo it, if you stretch it too much or you compress it too much, it will permanently deform. So this is where you run out of the elastic region, go to the yield point, and goes into plastic mode, and now you're permanently deforming the metal. Just like, again, take a piece of or a plastic shopping bag and stretch it over your knee finally gets the form of your knee, and it stays permanently shaped that way. So this is what we're doing. We're traumatizing the metal, stretching it so it grabs this shape. Okay, and this is an example of a wing. Oh, by the way, let me go back. Now, most likely the piece that we need is only this much right here. All this is excess, but we need the excess to be able to stretch on it. But the piece that we need that goes on the aircraft is only about that large. So we're going to have to recycle the excess material. I'm guessing this is the leading edge of a wing, or maybe the top tail or the top section of the tail of an aircraft or small aircraft. So once again, this one you're going to stretch in a different way, but it's the same idea. And most likely all this is excess and probably only need about this portion of it. Okay, so this is excess material that you'll have to recycle. All right. So I've been talking about tool design, right? So if you go into this field, if you like getting your hands dirty, you like working on cars, you like working in the shop, you may want to go into tool design. So I went from becoming a drafter to doing tool design. Okay, so I had no idea what tool design was, so I just learned. So 15 years ago, I started doing tool designs, very similar to these blocks, some of them even larger than this. Okay, so this is tool design. You work in manufacturing. You make the molds or the fixtures to make the parts or assemble them together. All right, so here's another example. A few years later, I went to work for this company that was making this large drone. So I came in to design these little fixtures shown in red. So I didn't come up with the concept, so I had a great supervisor. My supervisor would sketch, so it's very important to understand 2D drafting. So sometimes you have to read a drawing, sometimes you have to make a drawing, sometimes you need to sketch your idea on paper or on the whiteboard to get the point across. So my boss would sketch, hey, I need something like this. We're going to have to modify it. So this little red cart you see here, it's made out of steel. So before we put the aircraft together, it was just the fuselage. And before it was even painted, it was just carbon fiber. So it was just to roll the fuselage around the shop. And eventually it got assembled, the motor was inserted, the electrical, the wiring, etc., the fuel lines, the wings. This wingspan all the way across is 165 feet long. Okay, so I started modeling the carts. And by the way, in this case, my supervisor did not have an engineering degree. A lot of the designers that worked on the design of this large drone. So this drone is actually meant to be out. It's a step below a space satellite. They call these HALEs, hail drones or hail aircraft. These are high altitude, low endurance aircraft. So this aircraft has tanks. I can't remember if it was hydrogen or nitrogen. It probably was hydrogen tanks. And it had batteries. The batteries could last a few hours, but with the tanks and the altered car engine, it could stay up there gliding at a high altitude for up to a week. Okay, so this was an experimental drone. And my supervisor, so I want to pause here and talk about the different types of supervisors you're going to get. So a lot of the engineers that worked for this company, they had PhDs and masters and bachelors. I've had supervisors that had no engineering degrees, but they had knowledge working in a shop. So in this case, my supervisor started as a welder, worked for the big aerospace companies like Northrop, I believe also Lockheed Martin. So started as a welder and moved his way up and became a supervisor. And he would come up with ideas that others with PhDs wouldn't even think of. And it's because he had that shop experience. He had that welding experience. He put things together, assembled things together. So that experience that he gained working in the shop, it's something you cannot teach in the classroom. So I've had quite a few supervisors in tool design. They just had this bunch of experience. And even though they didn't have an engineering degree, I gave them a lot of respect for their knowledge. If you respect their knowledge, they'll take you under their wing and they'll show you and tell you what they want and help you develop as a designer, tool designer, for example, or as a drafter. Okay. And there's other tools that I designed here. Again, I did not come up with the ideas, but I did do the modeling. And by the way, this aircraft was started in SolidWorks, but there was, again, an issue with SolidWorks, so we had to switch over to CATIA V5. So they hired a bunch of us, contracts. I was only here for a year, so my contract was 1 year. Once the work ends, then they lay you off. But that's part of the contract world. Sometimes they hire you for 2 months, 6 months, a year. Once they run out of money or the project is over with, they'll lay you off, but they pay you good money and they pay you for the overtime. And these are just some of the hardware that I used on that cart. So this is a load cell for weight. This is a conic locator. So some of these pieces of hardware we used to locate it and also to weigh it because we wanted to know the weight of the fuselage. And also the weight of the fuselage with the wings. And here it is out on the runway. And again, here I designed this little trailer. Actually, it's not little, it's like about 25 feet by 25 feet. And again, my boss would sketch what he wanted, and I would do the modeling. One of the issues that we did have with this trailer was the wheels ended up castering, just like when you're in a supermarket. And the basket starts shaking because one of the wheels is castering all over the place. We had the same issue when it would hit around 20 miles per hour, so we had to add dampeners to it so it would stop shaking. That was one of the mistakes I made. Again, you're going to make, I have not mentioned this, you're going to make mistakes and you're going to learn from them. You're not going to design the perfect part. You're going to make mistakes and hopefully you'll have a good supervisor that'll guide you along the way. All right, so this trailer, we'll call it the taxi trailer. This was to move the aircraft from the hangar to the runway, or once it landed, we would go out there in the trailer and load it up. And the reason was because of the large wingspan, which allowed it to just hover over for a week, high altitudes. because of the large wingspan. A simple 30-mile-per-hour wind can knock it over because of the large surface area on the wing. So that's the reason we had to trailer it around. The trailer was double the weight of the aircraft, just in case a wind would come underneath, try to topple it over. We would strap the landing gear to the trailer. We would load it and strap it down, and hopefully stop the winds from knocking it over and have it shatter all over the runway. Again, these are some of the hardware I used. We used airbags. Once we loaded it, use airbags to lift it, just like the airbags you see on a car or a lowrider. Here are the wheels that I used. So we were having issues with the wheels start castering. They're just rotating all over the place once we would hit 20 miles per hour, pulling it with the truck. And some of the other hardware that I used. Okay, so once again, we're talking about tool design. If you guys like to get your hands dirty, then I recommend you go into manufacturing and tool design. By the way, also want to bring up again experience. Some of the best supervisors I've had, or the best engineers that I've worked with, had some type of hand experience, whether it was welding. So again, some of the best supervisors I had did not have engineering degrees. I do have an engineering degree, but the knowledge they had is just knowledge you gain while working in the shop. We're talking about 30 years experience. So the best supervisors I had were actually welders, and they just moved up the ladder, and they were really smart. And again, show them respect for their knowledge and they'll share it with you. All right, so another point I wanted to get to is, again, I mentioned working with your hands. So just as examples, besides welders, I had co-workers that were into cars and doing their own modifications. And from my current supervisor, he likes to take his own houses and remodel them. So hands-on experience to like our manager. Our manager, she enjoys working with rocket fuel. She likes to go out in the desert and launch small rockets to medium-sized rockets, blow things up. I had another coworker. She liked working with 2D and 3D art. So she would make 2D art and sometimes make 3D art, take pieces of wood and take a chainsaw to it. I had another young coworker. He liked to make personalized pens. So writing pens. He had a little lathe in his garage and would take wood, or it could be aluminum, and turn them to the shape you wanted and buy some of the additional clips you add to a nice pen. And he would sell them for $100 and people would buy them because they were custom made. So it's very important that you have some type of experience using your hands, even like something like making clothes. So if you like to make your own clothes, your own patterns, that's very useful for composites, like working with carbon fiber and fiberglass. So the more hands-on experience you have with something, even if it's something doing improvements around the house, for example, working on sprinklers, working on your car, for example, that's some good experience. And right away, I realized I didn't have much of hands-on experience. So I started buying project cars and working on them and doing modifications. And some of the knowledge you gain by working on cars, houses, woodwork, for example, some of that knowledge will transfer over. Hey, you know what? Something that I did to a car would work in this situation, working on this lunar lander, so. Okay, so for this example, this is something I did design. So another young engineer, a lot younger than me, started the design. He was so busy that he had to change to another project. So he had to finish up some other projects. So I took over the design. The surface changed, so I had to remodel a lot of this stuff. And there was a lot of details missing. So this is a bonding tool. Okay, so here's what it actually looks like. And this is to make this panel, this translating sleeve. And it's carbon fiber with honeycomb inside and another sheet of carbon fiber on the outside. So it's like a sandwich. So when you get on an airplane and you walk on the floor panels, those are most likely made out of carbon fiber. So a carbon fiber sheet on top, one on the bottom, and I think it's aluminum honeycomb inside to keep it lightweight, but yet make it stiff so it can handle the weight. Okay, so again, tool design makes the parts of the aircraft. It can be a mold or it can be something to assemble. Okay, so here's another tool that I worked on. So 3 of us. So in this case, our supervisor, who also happened to be a welder. So this is a whole different supervisor. Our young engineer did the modeling for the main structure, and everything from this parting plane below I modeled up. So I had to simulate the jet engine. So Boeing was going to use, I think it was a GE engine and a Pratt & Whitney engine, or a Rolls-Royce. It was going to use 2 out of those 3 engines for their aircraft. So we're going to attach part of the housing of the jet engine. This is referred to as a nacelle, in this case the thrust reverser. So I had to simulate the jet engine, the pylon, the fairings, the exit where the cone attaches on the nacelle. Okay, so I had to simulate a lot of the components in this area. So here's the wing, the pylon, here's the titanium cone at the exhaust. So I had to simulate some of this stuff just to make sure that when Boeing attached these components, the nacelle to the engine, everything did fit correctly. One of the problems was the wing was deflecting too much, so some of the parts were not lining up correctly when they attached the housing to the pylon and onto the jet engine. Okay, so the other group, so there was 2 teams, 3 members per team. The other team did a similar structure than we did. So this is the one our group did. So again, this is tool design. And here's their tool design. So this was for a different engine, same aircraft, just different engine. I forget who was using the GE engine. Others were using the Pratt & Whitney or Rolls-Royce engine. So just to give you a sense of the size of this. So on my design, I had to simulate all this, part of the jet engine. And this opens up, just like the hood of a car. Okay, so just to show you how far CAD can go, this is something I did design. So what you see here, I designed this fiberglass fuselage for this aircraft. So what skills did I need to be able to model this up? Okay, so this is where I was using a lot of CATD. So the class I'm currently teaching, so this is the CATD surfacing class. So a lot of the skills I learned when I first took this class 15 years ago, I applied a lot of the concepts I learned in the CATD surfacing class, which I'm currently teaching this semester. Another instructor will teach it next semester. So in this case, the aerodynamicists, we had 3 aerodynamicists. 2 were too young to be able to model this up, so they did a lot of the wind tunneling testing and came up with the airfoil shapes and the conic shapes, not only for this aircraft, but for another aircraft. And our senior aerodynamicist, he knew how to model and how to do the surfacing, except he didn't know CATD V5 very well, so that's where I got brought in. I'm not an aerodynamicist, but they would explain, hey, we need you to take these equations. So from here at the crown, from here to here, you're going to use this conic equation. So when you took, when you were doing graphs of parabolas and hyperbolas back in high school, and you're wondering, where am I ever going to use this? This is where I used it. I was using conic equations, mostly the shape of hyperbolas. In other cases where I worked in other parts, I've used the equations for an ellipse, for a circle, a parabola, hyperbola, or other conic shapes to be able to create the surface. So now when I first took over this project, somebody had already done a lot of the modeling. And I don't know if the project was temporarily placed on pause. So they told me to take over. And they told me, hey, we're not sure if the previous designer created this correctly. So we need you to recreate it because we can't not rely on the previous design. So even though the other designer had already modeled up the front end, the cowl section, the tail section, and part of the wings, it was incomplete and they weren't sure if it was correct. So I had to remodel everything from scratch. doing surfacing. In CATIA, another common software that's used is Alias, A-L-A-I-S. In this case, I ended up using CATIA Generative Shape Design workbench. And it took me about a month to create it from the drawings and the equations I was given. And I ended up getting exactly the same result as the previous designer. Then it took me another month to make changes. So the reason I was remodeling the surface is because this aircraft is all aluminum skins. Remember, we're talking about stretch forming? And they would have to rivet all these aluminum skins, all these patches around the wing, the top. You know what? It's simplified by making one fuselage, make it composite. In this case, they went with fiberglass just to speed things up. And in the assembly line, it was just easier to attach a fiberglass skin, very lightweight. Instead of having to patch all these aluminum pieces, it's like sewing, like putting a shirt. It's like tailoring a shirt or a jacket or a suit. Same idea. Okay, so after doing the surfacing, I did a lot of the tooling also and the drawings, and also had to redesign the doors. The doors were too short. So in order for the passengers in the back to get out, the pilot had to get out. So they told me to make the door 5 inches longer and a lot taller, just so it was easier for the passengers in the back to get in and out. The original aircraft only had one door, so they told me to add a door to the other side also. Okay, so, and it was all out of fiberglass. So a lot of the aluminum components got replaced by fiberglass. Okay, so here is the lightweight tube. Forgot the type of steel we were using, but this was very thin steel, thinner than a credit card. So this is the roll cage. So here's the fiberglass fuselage, and it was very lightweight. One person could carry it, and it was very flimsy, but once you attach some of the hard points on the roll cage, then it made it stiffer. All right, so just some examples. So some of the work that I actually did work on. So after I got done doing the surfacing, I had to do the 3D modeling. Right, so it took me months to work on this. I've never done a fuselage. I had no idea what I was doing, but I had a chief engineer and an aerodynamicist that would tell me exactly what they wanted. My skill was to do the advanced surfacing modeling. That was my input, that I can model fast and I can do complex surfaces. Here is the tool that I designed. I did not design the frame. This frame that's in the background, one of our young engineers designed the frame. I designed the mold. So this is fiberglass. In order to make the fuselage, you had to do it in two halves, the right half and the left half. And here is the door frame and the window. Okay, so we had to account for the window rebates or the joggles where you're going to place the window. And also you had to account for the hinges. Okay, so here it is at test flight. And again, I also modeled the doors. And we had one of our young engineers do the tooling for the doors, similar to this one. Actually look very similar to the door here, the door frame. And here's the final product. Doors are 5 inches longer, 2 doors, not just one, so it's easier for passengers to get in and out, and also for the pilot. All right, so here's this is a year after I started. Or maybe 2 years after I started, they were already flying this aircraft with the new fiberglass fuselage. Okay, this next aircraft, same company, but this is a new aircraft, carbon fiber. So the previous one was like taking an old Camaro or old Mustang and doing some upgrades by adding some composites, in this case fiberglass, to make it lighter or to make it look cooler. In this case, this is a brand new aircraft, carbon fiber, mostly carbon fiber. And this is maybe like a $500,000, $600,000 aircraft. And this is for training pilots. So here's the experimental. So I came in after I finished with the other project. I came and started helping out with this project, which was almost complete. So I did get a chance to work on some of the experimental parts of the aircraft. So I had to redesign the horizontal stabilizer and the rudder, and also some of the attachments at the belly of the aircraft. So for the experimental, they decided to make some changes to the rudder and the horizontal stabilizer. They wanted to be able to rotate it to find out which it was the best angle to place the horizontal stabilizer to make it fuel efficient. So this was a horizontal stabilizer you can rotate. Typically, you don't want to do that on an aircraft, but we only did it for the experimental aircraft. Okay, so I went from doing tooling to designing some of the structures of the aircraft. And again, I had never done something like this. I was new to it, but I could do the modeling and I could do it fast. As long as you have a good supervisor to guide you along, things should go well. Okay, now for the fuselage, how are we going to bond this carbon fiber fuselage? So because I had a tooling background, so how are we going to bond the left side of the fuselage and the right side to the primary structure? So this is not something I designed. This is from another company. So my boss told me, hey, go to their website. They actually have pictures. He goes, I worked here before. And I want you to design something similar to this where it bonds one side of the skin of the fuselage to the other. And inside you have the structural members. By the way, this fuselage is upside down. It's just easier to bond it together. And then later on, place attachments to it. Attach some of the components. It's just easier to work upward. Kind of like when you change your oil at a Jiffy Lube, it's just easier to work from the bottom up to change the filter and also pour out the old oil. Okay, so that's the reason it's upside down. So I did not design this, but I designed something very similar to it. I studied this picture on their website and other pictures for about 3 days before I finally understood how this worked. So there's actually some linear bearings here to slide things and close them up, some latching, and have the carbon fiber skins and structure bond together. Okay, and this is not the final aircraft. So this is what they were showing around at the air shows. Hey, we're coming out with this new carbon fiber aircraft, 2-seater, maybe 3-seater. Doesn't have an engine. It's just a model aircraft that you can take to the air shows just to show off your new concept. By the way, this project ended up getting canceled. I don't know if it was because it was a money issue, but the owner, she decided to cancel this whole project and just stick to the old aircraft, the old aluminum aircraft with the fiberglass fuselage. So this one, they're still producing. This new one got canceled. Okay, also there's electrical. Okay, so sometimes I'll get hired by startup companies. So there's a lot of startup companies trying to compete with Tesla. So typically they hire a lot of young, hungry, motivated engineers. You know, they want to work at the next Tesla. And you get a lot of hands-on experience when you work for a startup. You know, hey, we're working on this concept. You have young engineers out there in the shop, something that you don't get to do in a large company like a Boeing or GM or Ford or Northrop. When you work for a startup company, you actually get to go out there and play around and try things out, install things. Okay, so one of the things about startups is they tend to hire a lot of young engineers. They know the CAD, they know the electrical. I don't know electrical. Now, this is not something I worked on, but I worked on something very similar. So sometimes I get brought in just to make drawings. I don't know electrical, but I know how to make drawings. So a lot of young engineers, again, because of lack of experience, don't know how to create their own drawings. Takes a lot of years of experience. I would get brought in just to create drawings and get paid very well. I just never thought I would fall in the category of the old guy or the guy getting older that's now experienced in drawings and make drawings for us. So, this is the new CATIA. So I was talking about CATIA V5. Eventually we'll start teaching CATIA 3DX, the new CATIA. Imagine like taking CATIA, SolidWorks, and the best of AutoCAD and putting it all together. This is CATIA 3D Experience. So this is the software we were using at the startup company. So I would have something very similar to this, models like this. Sometimes I would have to make changes on the routing or rerouting of the wiring. Also, I made some of the attachments, some of the clips to attach the harness, the wire harness to the body of the vehicle. This is not something I worked on. This is just something from the internet, but I did work on something very similar. And creating a drawing similar to this one, right? And once you send out the drawing to the supplier, so in this case, I believe it was a company in South Korea. They were going to do the harnessing for us. So we would send them the drawings. They would print out the drawings and use a drawing as a template to do the routing and locate all the connectors. Okay, so this is a very easy way to create a wire harness. They're expensive. Those of you that worked on old cars, you have to order one. You know you're going to pay a few $100s in some cases. It's the amount of time it takes to create these wire harnesses. And again, you can see here in the background, you can see the drawing. They just follow the drawing to create them. Okay, earlier I talked about surfacing. Okay, let me take a step back. So we talked about tool design, right? So here's an example of tool design. Now, those of you that are very analytical, those of you that are going for aerospace degrees, mechanical engineering degrees, or structural engineering degrees, you're going to be the ones that are most likely going to be designing the aircraft. So when I got to design some of the components on the aircraft, I was working with the structures department. So a lot of them were aerospace or mechanical engineers. So I went from doing tooling to working as a structures engineer and also doing tooling on the side for the company. Okay, so I would jump sometimes from tool design to structures, structural design, and sometimes helping out the interiors group. Some of the young engineers would model the interior components, but they didn't have an understanding of manufacturing. So sometimes either I or some of the other engineers older engineers had to come in and make changes to their design so it was easier to manufacture. Okay, so when I talked about surfacing earlier, okay, so when I had to recreate this fuselage, I used a lot of wireframe, splines, lines, points, and parabolic, conic equations, very similar to doing like 3D hyperbolic shapes in 3D. So I use surfacing. So that's CAD 37. Let's go back to the list. So this is the CAD 37 CATIA surfacing. So when you do surfacing, typically you'll use Alias, ALIAS, a very affordable software, or most likely CATIA, the Generative Shape Design Surfacing Workbench or Freestyle Workbench. Now they have ICEM, ICEM. And so a lot of the surfacing in aerospace and automotive is done using CATIA surfacing or using that Alias software. Okay, so let's go back to the pictures. Okay, so we're going to talk more about automotive now. Okay, so we talked about tool designers. You like to get your hands dirty. Maybe you don't have an engineering degree or don't plan on going for an engineering degree. Go into a tool design. If you're very analytical, go into aerospace, get an aerospace engineering degree, mechanical engineering degree. Maybe you can also do stress analysis. You know, that's where you study if the structure is sound and it'll hold and can handle all the loads and weights and the gravity when something's flying out in space, for example, or a plane flying. And there's the creative side. So those of you that have the creative gene, okay, so some of you are very creative. You like to sketch. You like to work with your hands to make models, whether it's out of clay, out of cardboard, out of foam. If you have this creative gene, I suggest you go into automotive. Okay, so here's an example of a studio department. So when I worked at Honda, again, as a contractor, I was there the contract was 1 year, but I was there for just over a year. So Honda R&D locally in Torrance, they have their design studio, Honda R&D America in Torrance. And also Toyota had their design studio just down the street, but they moved to, I believe they moved to Texas. All right, so if you have that creative side in you and you love doing CAD work, you want to get a job in a studio department, whether it's Ford, GM, Honda, or one of these startup companies. Those of you that end up working in a studio department, you are treated like royalty. Okay, everybody wants to be in the studio department. You are kept separate from the rest of the company. You have your own cafeteria. You have your own break rooms. You have the best of the best. You are treated again like royalty. And the reason is because when you're coming out with the new concept, so if a new, for example, they're coming out with the new Honda Civic, they're coming out with the new Honda Pilot, new Corvette, coming out with the new Mustang, nobody wants, hey, you want to keep this concept hitting from public or anybody taking pictures. So even, for example, you want to make sure because sometimes we would see drones flying out the window and like, whoa, there's drones passing by. They're trying to get pictures of our concept cars, right? Now, it just happens that there was a company next door that made drones. They were not spying on us, but they're that secretive when they're working on a new vehicle. Okay, so if you have that creative gene, you want to work in a studio department. Again, you get treated like royalty. All right, so when you work in a studio department, you'll see these clay models. So underneath the clay, there's a structure. Just imagine maybe like an ice cream cone, and you pour chocolate over it, and there's a shell. In this case, it's clay. And underneath, instead of ice cream, you have a plastic, typically a plastic or a wooden structure. You don't want this to be solid clay all throughout. You just want to slap on the clay on top of the structure and start shaping your concept. Okay, so here's a very rough. So there you have the sculptors. Okay, here's a more detailed car. I think the previous one, I don't know if it was a Ford or a Toyota. Okay, so I did not work on any of these cars, nor did I work for any of these companies. But here's a more detailed clay model of a vehicle. And these are referred to as the stylists. I was calling them sculptors, but yeah, they're referred to as stylists. So here's an example of another clay model. Here's the structure below it. It can be plastic, it can be wood, and they just slap on the clay and start shaping and shaving away at it. And once they pretty much have their concept down, they'll lay think of like a window tint. They'll add this film, this grayish film. Gray seems to be the most common color to use, so they lay it over the clay, similar to laying tint on a windshield. Now these are actual components here, so this is a real grill, a real light, just to make it look more real, but this is a clay model. These are real wheels and rims. And you can see the concepts in the background. So first they'll sketch their ideas. You can see it in the background. And they'll use a full scale also. So if you have that creative gene where you can quickly sketch up a concept car or interior or anything like this, you may want to go into working in a studio department. Okay, so you want to be a stylist. Okay, so once you make the clay models, they'll take it almost looks like a small car wash, and they'll digitally record all the surfaces and store it in the computer. You'll see, I think it's a purple light. Looks almost like a laser that's scanning. So it's scanning the vehicle, and they'll turn that into a file that you can then open in Alias or CATIA. So the ones that were doing it by hand, they're the stylists. And we would be in a very similar facility like this, and we would be upstairs and we can look down, see how they're working on their vehicles. Then they would digitize the surfaces, record the surfaces, and then they would send the info to us, and we were the digital stylists. So we had to recreate their clay surfaces and remodel it, because even though it looks perfect, there's a lot of dips, it's not exact. There's some errors in the surface because, again, you're doing this by hand. So we had to recreate their surface using either Alias or the CATIA surfacing workbench. And they would also do clay interiors. Okay, so you have clay interiors. Again, here are the concepts. So typically the type of people they hire when they hire young interns, these are the young interns that enter competitions on, hey, creating the futuristic city of America, or creating the new futuristic flying vehicle, or flying taxi, for example. These are the type of interns they typically go out and look for, the ones that enter these competitions. Or they'll look for engineers that are studying to, or young engineers that are studying to be transportation engineers. So they like to also hire mechanical engineers, anything automotive related, or anything that involves sculpting or coming up with concepts. Okay, so once again, they would scan the clay models, digitize it, and transfer the data over to us, and we would have to recreate their same surfaces that they provided for us. Simple example, like on the Honda Pilot, I got to work on the headrests. So sometimes somebody would model the first one, and then the stylist would change their mind. No, you know what? We want to make them narrower. We want to style them some more. So sometimes they'll give the work to another designer. So sometimes I would take somebody else's work and redesign the headrest. And they would give us weeks to work on this. This is not something you did in a few hours. They would give us weeks to redesign a headrest. And then sometimes they'll take my work and give it to somebody else and change the whole design. Sometimes I would work on some of the simple parts like the seat cushion. Now, surfacing is probably the most advanced form of CAD modeling. Anybody can model a soda can, a cylinder, a rectangle. Surfacing is a whole different level. Okay, so it's advanced modeling. Anytime I'm in between jobs, the one thing I practice the most is surfacing. Another thing I got to design was the overhead console. And here I was given months to work on it. So I had to recreate the surface from the clay model. And working with the stylist, the one that did the clay models, one of the leads, he would explain to me, hey, this is what I'm looking for. Simple example, they would tell me, hey, you know what, these on the headrest, you know how you're making this an arc? An arc is not a pleasing shape to the eye. You need to make it more like a hyperbola. Okay, so anytime you look at a car, you don't want to see arcs. You also try and avoid straight lines. You want to give it some curvature. So here's an example. You don't want a straight line. You want something that look almost parabolic, hyperbolic, conic shape. It's more pleasing to the eye. You don't want to use a fillet, a constant radius. Like you don't want to use a constant, let's say 10-inch radius. You want to make it parabolic. It's just more pleasing to the eye. So that was cool about working with stylists. They would explain why they needed the shape. No, we don't want circular or arc. We want hyperbolic, parabolic. So working with these stylists, it gave me a better appreciation when you watch shows such as, Custom Garage or Bad Chat Customs, where you have these fabricators. They take an old car and they reshape it to something that's pleasing to the eye. I never understood when they would explain the lines of the car and the curvature, but after working with stylists and they start explaining why one shape like this shape here is more beautiful than a straight line, just more pleasing to the eye. Think of these stylists as artists. And one thing I discovered about myself working in the studio department is that I don't have the creative gene. I would always try and design things simple, fast, and nope, take your time and let's make it pleasing to the eye. They would always want more time to make it more pleasing to the eye, more beautiful as far as the surfacing. And once you were done with the surfaces, then you would send it to somebody to finish it up. So you just send the surface, and then somebody would model the actual plastic piece, the 3D model. Or if it was leather, for example, or aluminum. So our job was just to create the surfaces and pass it on to an interior designer. So I've also worked as an interior designer for automotive, where you take the surfaces from that was created by the studio. And now you're modeling the actual solids. Okay. All right, so once again, when you're doing surfacing, typically you're given a lot of time to work on it. If your supervisor or the stylist doesn't feel that you're getting the idea, they'll typically will yank the job from you and give it to somebody else. So it was very common to get something yanked from you and give it to somebody else, or it's given to you. Okay, so styling, that's where you want to be if you have that creative gene. Okay, where I'm currently working at, so this is the first time I'm actually working on a spacecraft. This is a lunar lander. So I worked on tool design for space satellites when I was at Northrop, ground support equipment. But now I'm actually modeling some of the structural members of this lunar lander. It's about, I think it's around 10 feet in length. So hopefully in a year or two, it'll be up there on the moon. So we're going to use SpaceX to launch it to one of their rockets to launch it up to the moon. And then on its own, it'll land on its own using its own propulsion system. So for my role here, I'm here as a structural engineer, and some of the components have already been modeled up. And by the way, for this project, we're using SolidWorks. So here the shapes are very simple. You have hexagons, you have triangular shapes, rectangular shapes, very simple shapes. So with this one, we can use SolidWorks. Okay, I know this was a long video, but hopefully I answered some of the questions some of you had. Maybe some of you found this interesting. Maybe some of you didn't. Maybe you found it boring. I'm open to any comments to improve this class. Hopefully some of you that didn't know which direction to go with your CAD experience or future CAD experience, maybe I gave you enough info on some of my experience that I could share with you. Anytime I'm asked in an interview, what type of engineer are you? And I don't mean in a bad way, what's your experience? I don't call myself a structures engineer, even though that's my degree, structural engineering, or an interior designer, or a surfacing, aerodynamic surfacing CAD modeler, or a tool designer. I consider myself a general engineer, meaning I'm not an expert in one area, but I know a little bit of everything. I'm not the best interior designer, but I can design some of the parts for the vehicle or aircraft. Same thing with tool design. Same thing with working with aerodynamicists. I know how to do the surfacing, or I can figure it out, or even they can tell me what they want, and I can figure it out on the CAD side. So I'm hoping that this helps you at least give you some direction. And if you have any questions or again suggestions, please let me know. So that'll be the end of this video. And on our next session, our second class session, we'll have our first assignment. End of video.